Hello, everyone. So, today we'll be talking. The past few weeks, we have been looking at a lot of assembly stuff, and we've been looking at different reverse engineering stuff, and then we kind of looked. We spent like 2 weeks working on like coding program in Nasm with on. So today we will actually be covering some coding conventions, like So I'm pretty sure everyone knows like there's certain coding conventions for like different languages. So if you're working in Java or C or any other language, you have like a something what they call coding conventions. Does anyone like to kind of raise your hand and give an example?
Don't There's capitalization of
Oh yeah,
things like don't capitalize their first letter and
yeah, capitalization and like
structure.
namings.
Yeah,
Anything else?
just how you structure your function names,
Oh yeah. So today
or
we're gonna.
all
Oh,
capitals or constants.
oh yeah, yeah. Constant. So today we'll be talking about some coding conventions in assembly. Why are we doing this? Because I thought in assembly we can do whatever we want. But here's why. There's three reasons that I like to put. Is that first of all, it's more cross-platform. So there's still like assembly is very platform dependent. So if you're using Windows or if you're using Mac or using something else or Linux, you have a very different way of kind of writing your code in assembly. So Nasm X helps with a little bit of that cross-platform issues. Um, and then next thing is less micromanagement. So I think I will that will be more self-evident when we go into the code. And then it's also a little bit easier to read because NASMX helps you put a little bit of structure into your assembly code. So first of all, we're going to talk about labels. This is actually not about NASMX, it's about NASM itself. So we have something called global labels and local labels. So basically, you have a global label. Those do not have a dot prefix to it. Local labels have a dot prefix, which means that actually these local labels are nested inside the previous global label. So I can go show an example. So here we have a label called global, and that is a global label. And then we have a local that goes under it. So then if we're jumping, if we have that jump instruction dot local, we are actually jumping the local label under global, right? So then now we define another local global label, and then we define another local label with the same name. But wait, isn't aren't we not supposed to like have labels of the same name? Right? If you're thinking that, that is true. Like you can't like global labels, you can't have two labels with the same name because that doesn't work. So the interesting thing with local labels is actually it's prefixed with this the previous global label. So in this case, the actual label name is called some other global dot local, and that is the full name of that local label. But then you can just reference it without putting tagging that global label in in the beginning of that. So this way, you can be able to create jump, like if you're having if statements and stuff or loops inside like a function, this allows you to be able to create labels that have the same name, and you don't have to prefix it with like the function name, and it's easier to write out local labels as compared to global ones. And also the last statement, we see this last statement, we see global dot local. So that is actually, since we are not actually under the global label anymore, we have to actually reference that. Like you have to do a fully qualified name. I think the comments are a little bit more they kind of document what it is. And also, I also have a cheat sheet that I did not print out, but basically I have that available, so that way it's easier to keep track of all this stuff. And then we go on to talk about procedures and calling conventions. So remember, what are calling conventions?
What registers you use?
Okay, registers you use. Does it tell you what order of registers you should use?
And sometimes you have to like zero out certain registers.
Oh yeah, yeah. So calling conventions are very deep. What's wrong with them? Like, first of all, it's very platform dependent. Like, you have different operating systems, you have different architectures. If you're doing 64-bit or 32-bit, they have different calling conventions. It is frustrating to memorize all of those. And then you also have to memorize what registers you have to pass, what order you have to pass. All of that stuff is annoying. And if you're trying to code in assembly, that's probably not the best way to approach things. So, how does Nasm X solve it? So, we actually in Nasm X we create we create a way of creating procedures. Remember, in Nasm or assembly, there is no such things as procedures. You can just define labels, and those labels point to like the beginning of a procedure. But with this addition, Nasm X actually gives you an abstraction of different procedures, and it allows you to invoke these so-called procedures. And then you just pass in arguments as you would like in a C function in a C program or in Java, which is a lot easier because you don't have to memorize what registers to pass and then what order to pass them in. So here's an example of how you would structure a procedure. So you see that here I started with the keyword proc. And then I have the name of the procedure, which is add nums. And then I have two arguments. Both of them are 32-bit integers, num1 and num2. And then I have a locals none, and then the three dots is basically where the code goes. So where I would put my code. And then I have an end proc. That signifies that that is the end of that procedure. This is actually not needed in like bare assembly, but with NASMX, it helps NASMX do all of the bookkeeping stuff. So now we talk about how to call different functions. So here there are different ways of you use the invoke keyword to call a function, and then there are different ways of passing arguments. So you can see here, for my first parameter, I passed in RAX, which is a register. And then my second parameter, I actually passed in a constant value, the value number 2. So invoke is actually very nice because it'll actually use the default call convention of the respective operating system and architecture. So you don't have to worry about that stuff. Of course, I haven't really tested it to see if there's some limits as to what registers you can pass without it kind of messing up. Because remember, we have to pass some arguments using registers. So if possible, I would stay away from using registers to pass in as arguments. Because there is always that potential that NASMX can screw that up. Huh?
When you call a function, do you always have to use the registers? Because I was looking at programs that were
Huh?
just pushing when you call a function. And do you always have to use registers? Or because I see sometimes where they
Yeah. So
push that.
that is the reason why you see push is because you're on a 32-bit binary. Remember, with 32-bit binaries, you don't have as much registers. So they don't use registers because our registers are a lot more precious. So we don't use them to pass arguments.
Only 64-bit.
So only 64-bit has the register passing thing. Like in 32-bit, you would actually push the arguments in like reverse order. And then that's actually also kind of a mess trying to figure out which ones to push. So here, how do we now we define like our procedure? How do we get arguments off of that when we define a procedure? So we use a inline macro called argv, which allows us to access a argument. So how you do it is you add a dot to the name of the argument that you named it, and then you would surround it with square brackets because you're accessing it from memory. So do we have an example? Yes, we do. So here, I went with the previous example. So here, this is the complete example of adding two numbers. So I have num1 and num2. And then I move the first value, the first number, into EAX, and then I add it to the second value. So you see that when we're using that inline macro, we're actually just accessing some memory. And if you remember from last week, this memory is actually somewhere in the stack using like an RBP register or something, RBP offset. But all that is taken care of in that macro. So we don't have to care a single thing about that. So it's very useful. So now we talk about local variables. So we talked about arguments. Now we have to, what if we want like variables for like a function? So we can use them to hold states of a function. And if you remember from last week, these are actually stored in the stack using offsets of BP or SP. And then if we actually just use it from the stack, like we try to manually code in the offsets, it is very error prone because first of all, they're not named. And so it's difficult to keep track which variables are in which offset, and you can actually accidentally overlap these variables if you don't know if you kind of screw up the sizes of the registers or the variables. So yeah, we want to have some way to automate that. And again, Nasmx has a way to solve it. So we have to define these local variables within a proc and proc statement. So that has to be there. You define all local variables basically at the top of your code before you put any other code. If there are no local variables, then you type in locals none. Otherwise, you'd use locals and then n locals to define a set of local variables, and then you use the var inline macro to reference these variables. So here is another example. Here, what I have is I actually have a subtract function, and I pass in two parameters, which is strings here. So ptrdiv is just a pointer type. And then what we have here is we define one local variable that is a 32-bit integer. Note that it is actually kind of interesting how NasmX sets up how you're defining arguments variables. With arguments, you have type name, then your argument, no commas, and then you just comma the arguments, list of arguments. This is very similar to how you would define functions in like another language. But note, when you're defining local variables, you actually have variable first and then type with the comma separating it. So it is kind of different. And so just beware of that. And then we have an invoke. So we first invoke a2i, which is a string to integer conversion function. So it converts a string into an integer. And that is actually returned in EAX as per se in most calling conventions. And then what I do is I read in the second number first, and then I do a subtract from the first number. So the first number minus the second number. And that will actually be automatically returned in EAX. So now I think that is it for like lecture. It was very short. But so here I will actually figure out here today I will actually be coding in Windows because probably more people would more likely be working with Windows. So I thought it would be nice to kind of work with it once because there's also some differences between using Windows and Linux and Mac. So I feel like it is good to kind of work with all of them. And excuse me for a moment. I need to figure out charging my laptop. Okay.
Oh,
This is Nasm. So, and then this one you can actually download with Linux as well, but not with Mac, unfortunately. So here I have a new thing open. So one thing to be certain is I actually have a few preloaded stuff on it. So first of all, I have this installed. I have a Nasm X, which is like a zip file, actually copied. So if you search up Nasm X 1.4, you'll actually come up with the zip file, and then when you unzip it, you'll come up with an ink folder. I went over this the first meeting, but I think some people might not have gotten this, but the idea is there's an ink folder and it has all these nice stuff. I want to copy this into this location here. So under program files, I want to be able to copy it under SASM. And then there's an include folder. And then you just paste it right here. And this is for Windows. So here, I'll just go like probably what I'm gonna do is just write a program that reads in some integers. So first of all, I would like to include that Nasm Inc folder, and then I first define some boilerplate code. Okay, so this one I need to actually import printf. I think that's it for now. And I also need, let's do scanf. Why not? And I need to also say that the, what's it called? What was it called? The global, right? So global main. So this is kind of important because we want to make sure that, and then I can do proc main and then end proc. So right here, what we're writing here is we want to be able to get our main function, and this one allows us. This one, the global command will actually global directive will tell the tell Nasm to kind of export this main symbol, so that way we can actually execute it. And then this should compile. Of course it doesn't, because I think I misspelled Nasm X. And screw that. Let's delete that. Okay. And I also need a locals none, because I'm not defining any local variables, and it will compile. Hopefully it will compile good. Yeah. So now let's just do a hello world, because why not? So I want to define a section in the data, and then call it str hello, and then db hello world. And then here, so I have the string hello world. I have a 0xa, which is a new line, and the 0, which is a null terminator, which means to stop parsing anymore. That means the end of the string. So if I can invoke that, and then it should build and run. It'll actually output right here. So let's see if I could actually make it right there. So now you can actually see the output. Okay. So now we wanted to be able to read some data, because yeah, it's not, we want to be able to read some integers. So let's start with the do not import statement. This will import scanf, and then we'll define a format. This will be reading a integer from user input. So, and then we'll actually, so now, does anyone remember what we have to do in C to use scanf?
Get the format string and then an address.
So we need an address. So what is address to? Or
Wherever you want to use it.
so we need something to read it to. So like a variable.
Yeah.
So this is where we want to define a local variable. So here I can define some local variables. Local let's call it num, and int 32, and then I want to scanf.
What's the difference between procedure and like a label?
Okay, so proc is a really useful macro defined in Nasm X. So this one is actually a little bit more abstract layer. So the reason why you want to define procedures is in order to use Nasm X, and allows you to define local variables without having to worry about stack offsets. Like it will handle all that for you, and it will also handle like invoking other functions. You would require using proc and proc.
So you use these as your functions?
Yeah, those will be like functions.
So what is Nasm X exactly? That's just like a
It's a pack. It's like a some code. So think of it as like a header file with a lot of interesting functions and macros and all that stuff.
So it's better to use Nasm X than just straight Linux something.
Like, it's easier to start off using Nasm X because it helps you kind of a lot of the more tedious issues. It will help you take care of that. It'll do all of the bookkeeping and stuff. So remember when we had to do like the push RBP subtract from the RSP? That is all taken care of by Nasm X. So this one, you can just write pure assembly code that does what you want it to do.
So if you go to put this in IDA, does it, like you said, this takes care of like push RPP
Yep.
stack.
Yep.
So when you go to IDA, does that like, you don't see this part, you see what actually is going on underneath?
Yeah.
Thanks.
Although, yeah. So here I have a main, and I want to call, so invoke int scanf, and then I want to pass in this as the string, the first argument, and the second argument I need to pass in a pointer to our kind of variable. So var.num, something like that, I think. And it will read it to the local variable num. And we want to print it out to make sure this is actually correct. And let me just use the same format as before, and then we just print out like that. But this time we actually read from address. Oh, yeah. So the second one we're actually reading from reading from memory. The first one we're taking the address of. Also, is it kind of small? Can y'all see it, or do I want to zoom in? Huh? Okay, cool. Let's F9. And obviously that is not what it's supposed to do. Okay. Okay. Okay, yeah. So apparently you have to actually type in the input beforehand. Interesting. So here I type in some values, 1, 2, 3, 4. If I compile it, if I press F9, it will print out the wrong value. Oh, I know why. So this is just a file. So if I change this to the first line and then F9 to run it, it'll print out 1, 2, 3, 4. So it does what it does. So it's kind of it's not a terminal type interface. Good to know. So now this is kind of boring. We're reading one integer at a time. How about if we try to read like an array of integers? So we have two choices here. We can just define a segment in the data section and we put our array in that data segment, or we can also be a little bit fancy and decide to put that on the local variables. So what do you guys want to do? Okay, locals. So here, instead of defining local num int32t, I actually add another argument, a third argument, which is a count. This is basically like the array size. So let's say 24 into 10 integers look good enough, right? Just read in 10 integers and it will print that out. So let's rename it nums. So now we have an array of 10 integers on the stack. And then we want to write a loop to first read it. So now we want to figure out how we can pass that some array reference into that. So we need, what else do we need for a loop actually before we start going deeper into this? Loop control variable. So we need a counter, right? So I actually forgot that. So let's add a counter. Why not? Let's make it 32-bit as well. And then this is not an array. So first we want to initialize our counter to 0. So we do that using this. And then this will set our counter to 0. Next, we want to do a loop while the counter is what? Okay, less than 10. So what we compare, right? So we compare the argument. So this one, I'm just reading it. I'm just doing the compare in one statement. Or 10. Something. What do I compare with actually? Huh? Like how many times do I want to loop this thing? 10 times. So what do I compare with so that it will loop 10 times?
9 or 10, depending on where you increment.
Oh yeah, I'm probably gonna increment like right here. So add, yeah. So this one I increment 1 here, and then so what do we compare with? Okay, 10. So here, notice that I'm actually doing the statement, the reading in from memory and comparing in one statement or one instruction. I could also do this, which is also legal, which is two statements. So first I move into some temporary register, and then I compare RAX with 10. Actually, I have to do EAX because we're working with 32-bit integers. And I forgot I have to do this stuff. Don't forget to write your size when you're using memories, because I forgot that. Okay, so you have something like that. This works, or we can also just do that one statement. So, like these two are equivalent, but I think this one is probably maybe faster. So yeah, we have this statement, and then we do a jump. What is the jump condition? Equal to? But remember, we're jumping back to loop 1. So what is the less than? So less than, I think, dot loop 1. So something like that. So now we're reading it 10 times, I think. So let me. So now we have increment while CTR is less than 10, something like that. So now we are actually, this is our loop body. So we want to, first of all, we want to read our register. We want to read our counter into a temporary register. So let's just use RAX or EAX for that, because again we are working with 32-bit integers. So EAX, and then we have you can use the multiply to get multiply by 4 to get to the offset. But let me show you, there is an easier way. So we're using a LEA instruction. So we're moving that into EAX, and then we have an address. So we have var CTR, and that gives us the offset of the wherever our local variable is, or where the beginning of our array. So the first element of that array is here, plus EAX times 4. And that can all be done in one instruction.
You mean dot num?
What do you mean dot num? No, I have to use a temporary register for that. So,
But the start of the array is at num, not CTR.
oh, yeah. My bad. I can't type. Yeah. So, yeah, that should be better. Right? The reason why we can do this, actually, I think it's RAX, not EAX. But the reason why we can do this is in assembly, we have 3 different types of memory address accesses. We just have like kind of base. And then we have some address memory like that, just from some absolute address. We have some register plus address offset like that. And that's often specifically used in like when we're accessing local variables, we have RBP plus some offset, which might be negative. And then we also have reg plus reg2 times some value. It has to be 1, 2, or 4, or 8. And then plus offset. So that one is actually what we're using right now. This is actually one of the we use this. This has this instruction because of these array accesses. It helps kind of it's a lot easier to encode, or like it's has you can encode it all in one instruction. And the basically the x86 architecture is designed to have a lot of these types of stuff. Although, yeah, it's actually a lot of micro instructions embedded in that thing. But yeah, we're using this type. So just like a little some if does anyone know what reg and reg2 we are using most likely using in this form when we actually assemble this, what would the disassembler output look like? Does anyone might have an idea what reg and reg2 would be for this next statement, line 30? So we know that we are accessing a variable called nums. And then we know that the RAX is the scalar one, and it's multiplied by 4. So what do you think reg 2 would be? It is RAX. What about reg? It's a little bit more tricky.
The top of the stack.
Top of the stack. So what register is that? RBP? Okay. Yeah. So what we have here is I was just kind of seeing how this form kind of matches. So I'm not actually doing something really crazy here. It is actually matching like a specific form in assembly. So that's the point of what I'm trying to get there. So no, you can't with this multiplier. You can't make some arbitrary multiplier like maybe times 3. That would not compile. It has to be one of these 4 multipliers because those are actually used most often. So, anyways, we use this LEA basically to do lots of memory math in one instruction. So now we have actually this should be RAX, not EAX. So now we have the address of the array at the offset at the index of CTR in RAX right now. So we just pass that to scanf. So we change that. We change the var nums into RAX. So that's what we have here. So now we go net. So I'm gonna erase this or delete this part because it might cause a bit of confusion. So this one is just read into array, and then we increment, and I think that's it. So this one will be reading 10 integers into our array. Now we want to print them out. So I'm just going to copy this because it's probably easier. So now we have some more code. So again, we just I think we just have to modify the loop body. You don't have to worry about all the other bookend stuff. So we change this to loop 2. Loop 2. And then we want to change. Now, we want to be able to pass a value into printf, right? So we're printing integers. So what do you think first of all, what instruction do you think we should use to read an integer? Like, you're getting a little ahead of us. We're just talking about what instruction. Move, yeah. Yeah, it's not that, it is simple. So now we move, and then you said about we use some brackets, right? Yeah. So we can actually just reuse these brackets that we have here, right? So what I'm going to do here is actually delete that, move it into EAX. So this time, why do we use EAX this time instead of REX like last time? Yeah. Yeah.
So it's 32 bit.
Yeah. Yeah. So last time, remember, we were actually getting an address of that that integer value. This time, we're actually reading that integer value into the register. So these are two different things. So now we call the invoke printf with the integer format. And I'm just gonna change that because I want a new line with I want a new line like I want like a new line so that way each integer is spaced accordingly. Okay, now we got that out of the way. So now there's also another note to make. When you're passing registers into invoke, if you're working with a 64-bit binary, we are not allowed to use 32-bit registers. I don't know why, but Nasm X will not allow us to do that. So here I am passing it as REX, even though we are actually passing in a 32-bit integer. And I think this compiles. Well, we'll see if it compiles. Num main. Oh, did I just define it as num? Wait, where did I define it as? Where did I use num? Oh, here. Let me delete that. Okay. So let's run. So let's just do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I think might work. Oh, hey, look at that. It works.
So back when you said using EAX when you're reading that.
Can you specify line number?
48.
48.
You said you use EAX instead of REX, but would it really have mattered if you use REX? Because isn't just going to see just put in the first 32 bits and the rest be zeros?
Well, I actually can't do that. So first of all, I specified the type as D word. If I do this, I think Nasm is going to complain to me. Yeah, it says misuse in operand sizes because the register REX is a 64-bit register, but then I'm only requiring 32-bit integers to be read. So it's actually, this is also another reason why you want to use named memory. You want to specify types with memory accesses, because first of all, assembly doesn't know like what types are you reading from memory. Is it bytes? Is it integers? Is it long? It doesn't know. So by using these type specifiers, it tells the assembly or it tells the machine that we're actually reading a 32-bit integer, not reading a 8-bit integer or reading a 64-bit integer. And then the other thing is to simplify like decoding, you have to also do a respectively same register size. So REX, or you have, in order to read in a 4-byte integer, you use the respective 4-byte register, which in this case has an E. So EAX instead of REX. So yeah. On the other hand, if we note here, this LEA is we're just taking an address of. So we're doing an address calculation. And that is just fits a 64-bit integer because we are in 64-bit mode and we have addresses that are a 64-bit. Make sense? So Actually, I feel like it kind of doesn't fit. So I'm just gonna change that new line into a space. So that way we don't have to make this really big. Okay, so yeah. This reads in 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, so we know that we actually read it correctly. So yeah. Let's see. What else do we want to do with this? So let's see this. So has anyone heard of the algorithm called longest substring, largest substring, wait, I don't think it's largest increase. No, I think like the largest sum of, like in the substring, you have the largest sum.
Cadence?
I don't know.
I think it's called cadence. But yeah.
Let me
Largest sum, array sum.
largest array sum. Yeah. Let me double check. It's just basically you go along the array, and if it goes negative, you just
Yeah.
make it 0. Yeah, yeah. So here, imagine we have an array. I'll type it here since. So let's say we have an array 1, 3, -1, -5, 3, 9, -4, -8, 15, or 1. So we want to be able to find a substring of numbers that gives you the largest sum. So it looks like probably 12 is the largest sum, but it has to be, these substrings have to be continuous. It turns out we can just simply go from the first number and then start adding them up. And then if it goes below 0, we just cross it out and make it a 0. So this is a very simple algorithm, and it's also pretty simple to code. So here, I'll actually just simply, we already have like a part that reads an integer, and it have a part that prints out integers. So what I'm gonna do is just pretty much just reuse this loop right here. Oh, I forgot to say print array, print number. So let me first save this so that if you want later. So this one would be called read test. Okay. So let's just do algorithm. So here I need like another variable, let's say sum, to like keep track of the sum that we have right now. And we want to set our sum to 0 because we want to make sure we initialize all our variables. That is a very critical part because our stack might not actually be zeros. Because if we call something, if the parent function that called something might actually have this part and stack might be something else. It might not be like zeros. So we want to make sure we initialize it. And I know in C, you cannot, it will actually warn you if you're using an uninitialized variable. And in Java, you basically can't do that. Like I think it will bark at you if you try to use an uninitialized variable. But yeah, in assembly, you don't get any warnings. So let's do the algorithm. So we start. Wait, why do we have this thing? Oh, I know why. Yeah, so that's a counter. We want to read our current integer. So now we have the value in somewhere in EAX. So let's just read read from array. We want to add it to our sum. And then let's move it. Let's move our sum into edx.
Can you not add it?
I think so, but you don't want to. You don't want to. First of all, we might have to do stuff with the sum before putting it back into sum, like checking it if it's negative.
Yeah.
So I want to put it. Actually, I could just do this.
Do it.
AX. That's probably easier. Yeah. So I add the two numbers together. So now if I say if it's compare if it is, what do I do with the compare?
Oh, don't you need two variables then?
Oh yeah, and then the largest sum so far. So I also need another variable according to on. So best, something like that. Okay, this is gonna be a little bit longer, but we have best. So we add the sum, right? We what do we do next?
Compare it to 0. Or
Okay, we want to compare with best. Okay, that worked. So we want to compare this with best, right?
So you don't need to compare where you have to say how much bytes.
Huh?
You have to specify how much bytes you're using in comparison.
Yeah, compare you're accessing your memory, so you're also specifying the number of bytes.
Whenever you do anything in memory, you need to specify how much bytes.
Yep. Yep. So now we are comparing. So what do we do?
you're gonna jump for 2 spaces with 2 lines.
So let's call this bad. So
And with the comparison, it's going to do subtraction. So if it's greater than, is like a zero flag? Is it just goes by the sign?
it goes by the sign.
So it'd be 0 if it's greater than.
So like in assembly is actually sets a number of flags. One of them is a sign flag. One of them is an overflow flag.
Yeah, so it sounds like 0 is greater, right?
Not necessary. It actually uses the sign and overflow flag together to determine if a number is greater than the other number. It's a little bit more complicated because there are edge cases where it kind of overflows and stuff. Okay, so we want to compare. I think we're almost there. So we want to compare. So let's say if best is already good enough, then we jump into
So jump
greater or equal to, like something like that. Yeah, I think so. And then if sum is better, then we just move it into best. Something like that. EX. Okay. Now the next part. So we.
When you say jump greater than, are you saying that the sum you just calculated is greater than the best? So wouldn't you want to?
Wait, what?
So line 57, you're saying jump greater than if. So you're saying jump if the sum is greater than best, right?
Yeah.
But
Oh,
if the sum is greater than best, then don't you want to write that value into best?
Yeah, that's probably correct. So LE. So if it's less than or equal to, then you jump. Yeah, good catch. Okay. So the next thing is we want to. So if sum is negative, we want to reset to 0. Then reset to 0. Right. So what do we? So compare EAX with 0. So
do the check case.
Why do you not just move 0 into EX?
no, because what if EAX actually is bigger than 0? Then you just reset it to 0.
So you use a comparator setting?
Wait,
It's like a if case.
it's an if case. So we're saying that if the sum is negative,
Oh, you're right.
then we reset it to 0. Yeah. So we compare if EAX is 0, we compare EAX with 0. So jump something not negative. So something. So first of all, I'm gonna do that. So jump greater than?
Yeah.
Yeah.
And then the next line would be move 0 into
Something like that.
and then move
Okay. So you can do that, or you can just do something even more fancy, X or EX, EAX. That also zeroes it out.
Which one's quicker?
This one's probably quicker because this one has less instruction bytes. Because 0, you're actually coding a 32-bit integer into the instruction. This one, you're just having 2 bytes, I think. Okay, so this one is a slight bit faster.
and then move
1
EX.
nanosecond?
Maybe. So now we want to move the sum, the value of EAX back into sum, no matter what, right? So I think that looks good. And then we want to delete that. Actually, I'll cut that out. And then we'll jump to the loop. And then we want to print the best value. So here I am just reading in the best sum. And then I have this label because I'm going to say best sum somewhere. So this one will be db best sum, and then 0xa 0. Okay. Oh, shoot. Oh, well, I kind of overwrite that. We'll fix that later. I overrided the read array test. Oh, wait, what did I do? Okay. So let's make sure it compiles and runs. Wait. Best sum 55. I think we can all say that is 55. Let's do something more interesting. Let's add some negative numbers in here. So 1, 3, -1, -5, 3, 9, -4. Does anyone want to give me some numbers?
-1
Okay, we have one more number. What should this last number be? 0. Okay, F9. Best sum is 12. I think we all agree 12 is correct. Okay, the algorithms works. Let's say if I say maybe 15 is the last one, right? So 15 should be the correct answer.
16.
Why 16?
No, 16 should be the answer.
Oh, yeah, 16. See, human algorithms don't do as well as computer algorithms. Okay, yeah, it says 16. So, and yeah, that is coding in assembly. And what we have here is, notice that when we previously saw it with assembly, we had to actually figure out, we had to write the boilerplate for like the push, REP, and the return. Notice how we don't have the ret instruction, nor do we have leave instruction, nor do we have any of that other stuff. So this one helps you get rid of all that junk underneath the rug. So actually, I can actually build this. Let's save the exe, but we can. I actually have an IDA on here, so we can actually look into it, see how it actually looks. Um,
Do companies actually write full program in assembly?
huh?
Do companies actually write full program in assembly?
I don't think so.
I think so.
Like, assembly is good, but it's tedious. Who writes assembly?
Maybe if like phase 8 brute force something and then faster.
So we called it stuff, or I called it stuff. So here I have IDA. So we notice that we have that push RBP and move RBP. We have a subtract. This one subtract, right? And notice that we actually, I think this is a subtract 40, hex 40. Yeah. So it's a little bit. Nasm X does a little bit more ornamental stuff. Like you can see the jump, this thing. You have a lot of other stuff, but we can see that it pretty much follows similar format of like preparing the stack and stuff. And then I think Ida is complaining to me how this doesn't kind of work the stack, but I don't care. And then we have this add RSP40, and then like it will pop the stack, and it will return. So this is how it looks like in assembly. You see, it's a lot more. It has the same thing, but then NASMX just hides most of that more low level stuff from you, and you can actually write in assembly. Okay, I think that's about it for today, and I think it's a little bit long, but yeah. Okay, let me stop this.